We're living in a world that's just, well, increasingly run by smart technology, aren't we?
Absolutely.
I mean, think about spam filters that just get it, or AI helping out with medical diagnoses now.
And those recommendations online. Sometimes a bit too accurate, maybe?
Exactly.
No.
So let's maybe unpack this a bit, because underneath all that smart stuff, the real engine is often probability.
That's right. And for this deep dive, we're looking at your sources covering, the different ways machines actually learn and make these predictions.
Okay. And our mission, let's say, is to really get our heads around the core concepts, the fundamentals, without needing a PhD in math.
Sounds like a plan. Keep it accessible.
Brilliant. So let's start super simple. Probability, at its heart, it's just the chance of something happening, right?
Mm-hmm. A number between 0 and 1.
0, impossible. 1, definitely happening. Like flipping a coin.
Perfect example. Heads or tails, 50-50 shot, 0.5 for each. Pretty straightforward.
So why is this simple idea so crucial for machine learning?
Well, fundamentally, machine learning algorithms are trying to make predictions. They look at data.
And try to guess what comes next.
Exactly. Or classify something, and probability gives them a framework. It's the language they use to talk about uncertainty.
So not just guessing, but making an educated guess based on likelihoods.
Precisely. To say, okay, based on everything we've seen so far, this outcome is, say, 80% likely. It helps make smarter decisions when things aren't black and white.
Okay, that makes sense. Now, our sources mention two main ways of thinking about probability in this context.
Yep.
Frequentist and Bayesian. They sound a bit heavy.
They can sound academic, yeah, but the basic difference is actually quite intuitive.
Okay, break it down for us. Frequentist first.
Sure. So the frequentist view is all about the long run. Think about that coin flip again.
Okay.
If you flipped it like a million times.
There's a lot of flipping.
A lot. A frequentist would say the probability of getting heads is 0.5 because over those million flips, that's roughly the proportion of heads you'd expect to see. It's based on observed frequency over many, many trials.
Ah, okay. So it's about what actually happens if you repeat something loads of times.
You got it. What you observe again and again.
And then what about the Bayesian approach? You said it's more flexible.
Yeah, you could say that. The Bayesian perspective is more about belief. It allows us to start with an initial belief about something.
Like a hunch.
Sorta, yeah, a prior belief. And then as we see new evidence, new data, we update that belief.
So back to the coin. If I flip it 10 times and get heads every single time.
A frequentist might still say, well, the long run probability is still 50%. But a Bayesian, they might start thinking, maybe this coin is biased.
Right. They'd update their belief based on that surprising run of heads.
Exactly. They incorporate the new evidence. It's a way of learning and adjusting beliefs as you go.
Okay, now that feels very relevant to how AI might learn. This updating idea, it leads to Bayesian modeling.
It does. That's the core idea. You start with a prior belief, your best guess, before seeing the specifics.
Okay.
Then you get some data, some observations.
Right.
And you use something called Bayes' theorem, which is the mathematical engine for this to calculate your updated belief, your posterior belief.
Can you give us an example? Maybe the medical one?
Sure. Imagine there's a rare disease. Your prior belief that any random person has it is very low.
Makes sense.
Then that person gets a medical test and it comes back positive. That's your data.
Okay, new evidence.
Now, tests aren't perfect. They have false positives. So Bayes' theorem helps you combine your low prior belief with the positive test result, considering the test's accuracy to get an updated probability that the person actually has the disease.
I see. So you don't just take the test result at face value. You weigh it against how likely it was in the first place.
Exactly. And that whole process of updating beliefs using Bayes' theorem, that's called Bayesian inference. It's super powerful.
And these probabilities, they often connect, right?
Mm-hmm.
One thing affects the likelihood of another, it sounds like. Bayesian networks.
Spot on. Your sources mention these, and they're a way to visualize and calculate these interconnected probabilities. Think of it like a web or a graph.
A map of influences.
Yeah, a map showing how different variables affect each other probabilistically. Like maybe having a fever increases the probability of having the flu, and having the flu increases the probability of having a cough.
Okay, so you can model these chains of influence.
Precisely. They're used for complex problems. Medical diagnosis is a big one, figuring out diseases from symptoms.
As well?
Oh, tons. Spam detection, looking at patterns of words, senders, links, even things like predicting if a car component might fail based on sensor readings or assessing risk in finance.
Wow, okay. So Bayesian methods are all about updating beliefs and understanding connections, but the sources also brought up something else. Support vector machines, SVMs. That sounds different.
It is, yeah. It's another really powerful tool in the machine learning toolkit, but it tackles problems, especially classification, from a different angle.
Classification meaning sorting things.
Exactly. Sorting data into different categories, like, is this email spam or not spam? Is this customer likely to churn or stay? SVMs are great at that, and also for some types of prediction problems called regression.
So how does an SVM do the sorting? Those sources mentioned finding a line or a hyperplane.
Right. Imagine you have data points plotted on a graph. Let's use the fruit vendor example. Maybe you plot fruits based on, say, color and shape.
Okay, mangoes over here, bananas over there.
Exactly. An SVM tries to find the best possible line, or in higher dimensions, a plane or hyperplane that separates the mangoes from the bananas.
Any line that separates them.
Not just any line. It looks for the line that creates the widest possible street between the two groups. It maximizes the margin, the empty space, between the line and the closest data points from each category.
Widest street. So the biggest buffer zone. Why is that important?
It makes the classification more robust. Think about it. If the line is right up against some data points, a small error or a new, slightly unusual fruit might end up on the wrong side.
Ah, I see. So a wider margin means it's less likely to misclassify something close to the boundary. Like separating fresh apples from rotten ones, you want a clear dividing line, not one where they're almost touching.
Precisely. The mathematical goal is to maximize that margin while still doing a good job of classifying the points you already have. Find the clearest, most confident dividing boundary.
Okay, that's a neat concept. So wrapping this up then, what's the big takeaway from looking at both Bayesian approaches and SVMs?
I think the main thing is realizing how fundamental probability is, even when the methods seem different. Machine learning often boils down to handling uncertainty and making distinctions based on data. Bayesian methods do it by explicitly modeling uncertainty and updating beliefs. SVMs do it by finding the most geometrically clear separation between categories. Both rely on probabilistic thinking, just, well, applied in different ways.
So it's all about using probability, whether it's calculating likelihoods directly or finding robust boundaries, to make sense of data and make predictions.
Exactly. It's the mathematical language that allows machines to learn from experience, essentially.
So maybe the final thought for you listening, next time your phone suggests the perfect next word, or an online ad seems weirdly relevant.
Or your spam filter catches that really tricky phishing attempt.
Yeah. Just maybe take a second to think about the probability that might be working away behind the curtain, constantly calculating and refining to make that smart technology work. It's kind of amazing when you think about it that way.